Now, water being a very special compound has some special acid-base properties, as we already saw how water can act as an acid or a base. And that means that if you have two molecules of water, one can act as an acid and the other can act as a base. So here one of these two is donating an H plus to the other one, giving us H3O plus and OH minus. This is not just a theoretical proposition of what may happen, but this actually happens. And here one water molecule is the acid, the other is a base, and both of them are very weak acids and weak bases. As a result, we show the reversible arrow. Now this is a reality, and water does this to itself. This is known as self-ionization of water. Water is a very weak electrolyte. In fact, it's so weak such a weak electrolyte that we saw in the reaction, we saw when we actually dipped in the electrodes connected to a battery, that distilled water or deionized water did not turn on the light bulb, because the concentration of the electrolytes on the right side is just too low. Yet this happens and it can be measured. To what extent does this happen? That's the question. Now here H3O plus, by the way, is called hydronium ion. And if you have pure water, pure glass of water with nothing dissolved in it and no salts in it, deionized water, in that water the concentration of H3O plus, based on this self-ionization of water which will happen, the concentration of H3O plus will be extremely minute, and to be exact it will be 1 times 10 to the negative 7 molar. Similarly, the concentration of OH minus will also be equal to that, because for every 2 molecules of water we get 1 H3O plus hydronium ion and 1 OH minus hydroxide ion. As we learned about writing equilibrium expressions, we can write the equilibrium expression for this, where we have H3O plus concentration times OH minus concentration in square brackets. We do not include liquid water because it's a liquid. Remember, in equilibrium expressions we only write down the concentrations of dissolved species like we see here. So what is the value of each of this? What is the value of the concentration of each? It's 1.0 times 10 to the negative 7 molar, and that's something that you should memorize. It's just a fact of life. And what is going to be the value of Kw now? The equilibrium constant expression for water gives you the equilibrium constant for water, also known as the ion product constant for water, and different textbooks name it differently, sometimes called the water dissociation constant, but it's the multiplication of the concentrations of both of these ions, which is 1.0 times 10 to the negative 7 molar times 1.0 times 10 to the negative 7 molar, and it gives you 1.0 times 10 to the negative 14. Because it's an equilibrium value, it's unitless, as we learned when we learned about equilibrium expressions, that the equilibrium constants are generally given as unitless values.